Hello everyone, this is Prashanth Reddy, Assistant Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering. We are in the lecture series of thermodynamics. In the previous video, we'll discuss about introduction to the thermodynamic thinking systems and various definitions in the thermodynamic systems and what is a process, what is a cycle, what is a point, and everything we'll discuss. And applications of thermodynamics where we deal with the thermodynamics. These all we discussed in the previous video. In a coming series, we'll discuss a few more topics on thermodynamics. In the definitions of thermodynamics, we have to know equilibrium conditions. So, while we dealing in the applications of thermodynamics, we come across with the equilibrium conditions. So, what is equilibrium? So, equilibrium indicates a state of balance. And equilibrium state, there are no unbalanced potentials within the system. So if there is no unbalanced systems are there, then we can call it as an equilibrium condition. So generally, if a system want to be in equilibrium, if the system is in chemical equilibrium, mechanical equilibrium, and thermal equilibrium, when all three together, if it is come across, then we can say that it is thermodynamic equilibrium. So when a system is in chemical equilibrium, mechanical equilibrium, and thermal equilibrium, then we can say that the system is in thermodynamic equilibrium. Now we'll discuss individual points on chemical, mechanical, and thermal. So what is chemical equilibrium? So chemical equilibrium means there is no any further chemical reactions happen in the system. If the system is happening while the system is doing that work, if there is no further chemical reactions are not there, then we can say that the system is in chemically in equilibrium conditions. Okay, so if you go for definition of this one, if there is no chemical reactions or diffusions of matter from one part of system to another, the system is said to be chemical equilibrium. And next, mechanical equilibrium. If there are no unbalanced forces, so generally we see that unbalanced forces are very major drawbacks in the mechanical systems. If there is no unbalanced forces we experience, then we can say that system is in mechanical equilibrium, right? So simple example I am telling. So there are some cases. If you see some systems, there are supporting systems are there. So there are this is a one supporting cases, and in middle there is a shaft. If you observe, okay. So after this extension of shaft, if you apply some amount of force in this one. So due to this force, there is a unbalanced forces are happening this one. So to minimize this one, what generally mechanically we do, we apply additional. That means to make it equilibrium, we do the extension for in the other end. We do the same amount of force in the other end. That means to make it equilibrium, we do the additional force on that one. That is in a second. That we call as a mechanical equilibrium. And the third one is thermal equilibrium. So, if a system is equilibrium, that means if it is an equilibrium condition with the surrounding systems, okay, in the form of temperature or heat, then we can say that it is in a thermal equilibrium. So, if you see the definition of this one, when a system is prevailing in a chemical and mechanical equilibrium, is separated from the surroundings by diathermic wall, and if no spontaneous changes in any property of the system said to be in thermal equilibrium. Okay, these are the equilibrium conditions. If these equilibrium conditions are all three satisfied, then we can call that thermodynamic equilibrium. Next, so there are a process, right? We know that there is a process and there is a cycle that we discussed in the previous. But now it is one more thing computed here is quasi-static process. So what is quasi-static process? Simple, we can say that quasi means almost. That we can also say that in other way it is a slow process. If it is any system very slow and almost slow, or approximately we say the very slow process, then we can use the quasi-static process. Okay, quasi means almost. The meaning of quasi is almost, but quasi-static process we can say that it is the process of infinitesimally slow process that we call as a quasi-static process. Okay, so it may be of reversible process of any way, but it is a quasi-static process. Okay, so I am considering a system which containing a gas in a cylinder. Okay, I am doing some experiment on this one. So I have some system. Okay, take example of this is a piston and cylinder. Okay, in this, so assume this is a piston, this is a cylinder. In this piston and cylinder, okay, in this piston and cylinder, what I am doing is I am keeping a some amount of weight here. I am keeping a some amount of weight. So due to that weight, what happened? If it is initially this position, it reaches to this position. That means due to the weight, whatever added in that one, inside the gas is compressed. That means volume of that one is come down. So the final volume is only this much. Okay. Now what happened here is I am adding at a single weight at instantly. Due to that, what happened? It having some process. If I draw PV diagram for this one, so I can draw the PV diagram in this way. So first condition is what? At the initial condition, volume is a V1 if you take, and pressure is P1. So combination of point I can take it up. This is the first point. Next, at the second stage, because of addition of weight, what happened? It reaches, that means volume of cylinder is come down. That means air occupied in a cylinder is come down. That means volume come to the position of V2, and due to the volume reduction, what happened? There is a pressure goes on increases. That means pressure increase to this place. The mixed point, I can say that this is one. Okay, what happened here? If I draw the connection point to both, it is happened like this one. This is a point. This is you call as a process. From 1 to 2, you call as a process. This process is we call as a compression. Okay, here what I'm done at instant of time, I directly add a some amount of weight. Due to that, I get some points of 1 and 2. So this is happened. But now I do the same experiment in different way. So what I'm doing here is, so same experiment I do the second way. So what I'm doing, same piston and cylinder. Okay, at a position of some position. Okay. Now instead of adding up all the weight at a single instant, I add a weight slowly. That means whatever the weight I added, same amount of weight, instead of that one, I add a single by unit. That where the previous weight I do the slices, I do the number of slices. Due to that, what happened? Slowly one by one weight is added in this one. Okay, due to the addition of weight, what happened? The volume comes down. So now instead of all the weight at a single time, I added a weight into number of slices. Okay, so due to this, what happened? It is now previously at a single instant I done. Now what am I slowly doing this one? So due to that, what I'm doing is I am at each individual weight addition. In this case, I draw the points. That means at initially the point is V1 and P1. Okay, next it is a V2, P2, then after it is a V3, P3, and next V4, P4, and V5, P5, like that, V6, P6. Like that I get some points. Now I join this curve, a smooth curve I join here. Now from the point 1, 2, 3, and 4, 5, 6 has happened. This is the process. So previously it happened at an instant time. Now I added the same process now. So slowly adding off one by one weight. This is a process is called almost slow process, nothing but quasi. If we can say that example for the quasi. Right? So this is an example for that. Right? So everything is whatever I explained is same. So you can see the diagrams from here. So initially in the first case I added the whole weight at a single instant. Okay, due to that the gas inside that cylinder is get compressed. Okay, in the second case what happened, I do the same amount of weight, but instead of that in single weight I added a slices of weights. So this case what happened, it is slowly one by one weight is added in this one. Okay, so this is a example for the quasi-static process. Okay, if I draw same thing, what I've drawn previously, same thing. Previously it is a 1 to 2, is a direct single points. Now, in the second case, I added the number of intermediate points. Due to that, I get the smooth curve. But here in the previous case, what happened? This is only line diagram I can get, because I cannot guarantee that it may be of curved one, it is a polytropic process, or it is maybe a logarithmic process. We don't expect that anything, right? So this is an example for the quasi-static process. Next, one more criteria we, as in the definitions of thermodynamics, a reversible process. Okay, so what is a reversible? And there is a one more term called irreversibility. Okay, just I give an example, then you can understand what is a reversible process and irreversible process. So I take an example of a waterfall from some mountain. So I have some mountain. Okay, so take example of this is a mountain. So over this mountain, the water is flowing like this one. Okay, water is flowing like this one. Okay, due to that flow, what happened? It is move from a position 1 to it reaches to the position 2. Right? This is a only one process. Can I do the reverse for this one? It is naturally it is simply impossible. Okay, so to get the same amount of water back to that, it is simply impossible. So here I cannot take this water backside. That's why I can call this as irreversible process. That means I cannot take the same water back until unless by using a external agent. Right? So that is we call as a reversible process. Now, so that is called as irreversible process. Now come to the reversibility. What is reversibility? So if any system, if you get it back, the same thing happened again, then you can call it as a reversibility. Okay. Example, if you take any automobile engine, we can experience the reversibility. That means it go to the upside and get back again, bottom side. So it reaches to the top dead center, it reaches back to the bottom dead center. So like that, the piston and cylinder, piston is moves in between places up and down. Okay, so this is called as a from this position to this position it is moving, so that you can experience this is called a reversibility. So it reaches to the one position, then go back to the other position, come back again, go to there, come back again, like that. You get the reversible process. That you call as a reversibility. From this graph, you can experience the same previous quasi-static process. If you take an example of that one, same piston and cylinder if you take, in this piston and cylinder, you previously what you done, you added a number of slices of weight, right? You added a number of slices of weight on one on other, right? If you adding slices of weight, what happened? The pressure is goes on increases, right? If the pressure is goes on increases, due to that what happened? Volume goes to decreases. So it is a forward process. Same thing, if you slowly remove one by one, if you remove the one by one of a weight, what happened? It will get back to the same original position. So by this we can understand that you can reverse this process. So anything, if you do the reverse, then you can call as a reversible process. And there are a few examples. Okay. So if you go for definition of reversible process, a reversible process, also sometimes known as quasi-static process, that means it is a very slow process, we can assume that, in one which can be stopped at any stage and reversed so that the system is surrounding are exactly restored to their initial stages. That means any middle of point, if you stop and get back to that one, you can call it as a reversible process. Example for this one is frictionless adiabatic expansion or compression of fluids. So same thing, this is example what I take. So frictionlessly, if you compress the fluids or expansion of fluids, then you can give the example of reversible process. If there is a friction happen, what happen? You can lose the amount of work there itself. That's why we can call it as a frictionless adiabatic expansion of fluids or compression of fluids. Right? Next, frictionless relative motions. Like anything, it is a relative motions of the, then if it is a frictionless, then you can experience the reversible process. That means how much amount of input you give, same amount of output you can get it from this. Right? Expansion and compression of spring. So if you take a spring, what happened? Okay. If you apply some load on spring, okay, if you release, then what happened? It gets back to the original position. so that it get the original position of that one, so that you can call it is a reversible process. Okay, isothermal expansion or compression. Okay, any isothermal process expansion or compression process is example for the reversible process. And polytropic expansion or compression of fluids and electrolysis. So in electrolysis, what happened? There is a membranes are there. Okay, while discharging, the electrons are go from one place to other place. While it is charging, it get back to the original position. Like that, we have electrolysis process, right? Same we can come for the example for the electrolysis process, that is called a reversible process. These are called the reversible processes. Next, irreversible process. So we know that just before I will discuss anything which we cannot get to the original position, then we can call it as a irreversible process. Okay, if you take a definition, an irreversible process is one in which heat is transferred through a finite temperature. Okay, if it is a heat, if you take example, if it is a transfer to the finite temperature conditions, then you can call it as a irreversible process, that we cannot get it back again. So example for this one is relative motion with friction. Okay, any motion which is having a friction motion, then you can call it as a reversible motion. Okay, irreversible process. Combustion. So combustion is also come for irreversible process. Once a fuel and air burns, burning will happen, then you cannot get separate a fuel and air separate, right? Once the burning happen, you cannot get it back. Okay, that is also come for irreversible process. Next, diffusion, free expansion, throttling. These all come for the irreversible process. And one more important thing is that heat transfer. Heat transfer also one of the irreversible process. Right? These all comes for the irreversible processes. Right? Next. Okay, there are two classifications are there in a irreversible conditions: external irreversibility and internal irreversibility. Okay, in external irreversibility, these are associated with dissipating effect outside the working fluid. Okay, if anything happen outside of the fluid, we can call it as a external irreversibility. Example, mechanical friction occurring during the process due to some external forces. Any mechanical friction happened there, then we can say that external reversibility. If it is an internal reversibility, these are associated with a dissipating of effects within the working fluid. Okay, anything happened within the working fluid, then you can call it as a irreversible. If you take the example of this one is understanding, that means expansion of gases and viscosity and inertia of the gases. You can take the example for this one, right? This is types of irreversibility, right? After these basic definitions of thermodynamics, two major forms of energy is we have to discuss. So there are two major forms of energy which we frequently discussing in thermodynamics. One in that is work, other one is heat. Work and heat both are two different forms of energies which frequently we discuss in the thermodynamics. So we generally understand in a basic understanding of studies, we can understand what is work and what is heat, right? And in a first day, in a previous video itself, we discussed, when we discuss the thermodynamics, it is a mixture of two words, thermo and dynamics. Thermo and dynamics. So thermo means which anything happened by using a heat, you can call as a thermo. Which by using the heat, any mechanical work, that means force with respect to some force will getting some amount of force will getting with some amount of distance. Okay, that we call as a work. That means dynamics. Okay, so here both heat function is added and the work we are getting from that heat. So that's why these two terms are very mostly we are here and familiar in the thermodynamics. Okay, so we'll discuss what is work and what is heat. Okay, next, what is work? Generally we know that it is one form of energy Okay, we can also define it. Work is one of the basic modes of energy transfer. Right? You are carrying some weight. You are keeping a weight, some load from one place to other place. You are picking some object and keeping some other place. This is all comes for the work. Okay. So in a mechanical perspective, okay, an automobile or in any vehicle, it is moving to the some distance by using some amount of force. That is also come for the one form of work. Okay, so this is a one form of energy. Okay, in mechanics, the action of force on a moving body is defined as a work. Okay, some action of force on a moving body we can also call as work. The work is done by a force as it acts upon the body moving in a direction of force. Okay, in thermodynamics, work transfer is considered as occurring between the system and surroundings. Okay, in thermodynamics, in a mechanics point of view, we'll discuss work is like this one, and in a thermodynamics point of view, we'll discuss work is like this. That means in thermodynamics, work transfer considered to occur in between the system and its surroundings. So work, whenever you discuss in the thermodynamics, it also have a considerations in a system as well as its surroundings. Okay, so there are two conditions we have. Work is said to be done by the system if sole effect on the things external to the system can be reduced to the raising of weight. Okay, so this is a basic understanding of work, and we can also say that work is done by the system. It is taken to be positive, and when work is done on system, it is taken to be negative. Simple. We can understand this one in such a way that, so when you are doing a work, okay, you are doing some work. Okay, I'll take some system. Assume this is a system. Okay. So what I'm doing, I am getting some work from the system. Okay, I am getting a work from the system. Okay, while I am getting some work from the system, I can indicate in a mathematically the positive. Okay, I am taking some work from the system. I can take it as I can call it as a positive. And some case, I am giving work to the system. So thermodynamically, I can say that this is negative. So I give the example for this one. So example for this one is, see, I have example. I'm taking a IC engine. Okay, take some IC engine. So the function of IC engine is internal combustion engine. Example, you take any type of IC engines like petrol engines or diesel engines or gasoline engines, okay, or gas turbines or jet propulsions, anything you take internal combustion engine. So by internal combustion engine, what you get? You get some amount of mechanical work, you'll get a output. Okay, so mechanical output, you'll get some output. That you call as a work. From that system, you are getting some work, so that for that system, it is a positive. Right? Same thing. Take an example of refrigerator. So in a refrigerator, to run the refrigerator, you are giving us amount of work input. You are giving us amount of work input. So to run the refrigerator, you need some mechanical work input. That you can call as negative. Why? Because for the refrigerator, it is negative. Okay. So for the same refrigerator, I club this one once again. So I am clubbing this one in such a way that, so I have a refrigerator. Okay. So don't confuse for this one. Just I give an example on this one. So this is a refrigerator and this is a motor. Example if you take. Okay. I have two conditions, a motor and refrigerator. This motor is electrical motor, assume. This is refrigerator. From the motor, what we get? We get the mechanical work output. Okay, we'll get the mechanical work output. From the refrigerator, we will get the some amount of cooling effect that we call as a negative heat output. Okay, that is absorption of heat. Okay, so this is we want. Negative output only we want. Right? For this refrigerator, we are supplying a work. We are supplying some work to the refrigerator, so that we can call as this is a negative to this refrigerator. Whatever work taken by the refrigerator is negative. Whatever work supplied by the motor is positive. In point of motor, work is supplied to the external agent. That's why it is a positive to that one. For the refrigerator point of view, the work is absorbed by the other system, so that it is negative to the system. Same, if it is considered this is a whole system, so for one it is a positive, for other one it is a negative. So this is the basic understanding of work. Okay, whenever you discussing of real-time applications or real-time problem solving, then you are getting a while you are giving that it is absorbing some amount of work, means that you have to take a positive W. Okay, sorry, when it is absorbing some work means you have to take a negative W. When it is giving us amount of work means you have to take the positive work. So in our real-time applications, no one tell that whether positive you have to take or negative you have to take. But yeah, automatically you understand that whether it is giving or it is taking, you have to take. Okay, take according to the work, positive or negative. Right. Next, heat. So heat is also one form of energy. Okay, if you want to define a heat is defined as a form of energy that is transferred across the boundary by virtue of temperature differences. If you want to transfer the heat from one body, okay, this is take a body A, body B. If you want to transfer the heat from one body to other body, there must be some temperature difference. Okay, this is T1, this is T2. If you take that, if from heat is need to transfer from A to B, nothing but should be some temperature difference is there. So always if heat is flow from A to B means if you take this is A, this is TB, TA always greater than TB, then only heat is able to flow from A to B. Otherwise heat won't flow. Nothing but temperature at A is must greater than temperature at B. Okay, that is only tells by the definition of temperature and the definition of heat. So there should be some definitely temperature difference, then only heat able to flow. Right? The temperature difference in the potential or force, okay, whatever the temperature difference we can call as a potential of that system, or we can also call force of system, and whatever the heat transfer we call as a flux. So that means amount of heat transfer we call as a flux. Okay. Next, heat flow in a system is taken to be positive, and heat withdrawn from the system is called negative. Right? So I give an example for this one. Okay. So same IC engine I am taking, some petrol engine example, you take some automobile petrol engine, or we can also call it spark ignition engine in terms of mechanical point of view. So I take a spark ignition engine, nothing but petrol engine we can call, or gasoline engine we call. So what I am giving is, so I am supplying the heat to run this engine, SI engine, right? I am giving us amount of heat to run the SI engine, right? I am supplying the heat. So that's why I call this as it is a positive work. Nothing but for this IC engine, I am supplying the work. Okay. If the heat is flow into the system, is taken always positive. For example, if you take a refrigerator, okay, if you take the refrigerator, what is the function of refrigerator? It need to cool the surroundings, or it is cool the area includes. The function of refrigerator is that one. That means it need to cool. So while it is cooling, what happened? It is release the heat to the atmosphere. That means it is releases the heat to the atmosphere. That means it is losing the heat. Nothing but it releasing the heat to the atmosphere to cool this surface. Okay, that's why we indicate it as a negative Q. Okay, so while if I supply the heat to the system is a positive, it is if I remove the heat from the system we call it as a negative. Okay, same thing explained here. The supply flow, heat flow into the system we take as a positive, heat flow out of the system we call as a negative. Same here explained. It is a flow into the system is positive, flow out is called as a negative. Right? This is a both are heat and work. Right? Once we have a knowledge on heat and work, next there are a few types of heat conditions we generally have. Right? In that, one is specific heat. Right? Specific heat. So what is specific heat? Specific heat is defined as the amount of heat required to rise the temperature of unit mass of substance by 1 degree change in temperature. So I give the example for this one. I have a bowl of water. Okay, take this is a bowl of water. Okay. So what I am doing, I am increasing the temperature. That means I am heating this water. Okay, by using some burner or anything, I am heating this one. Okay, so here what I am doing, I am supplying the heat to this one. That means I am adding the heat to this one. Okay, so here the water is getting a, that means water is adding a heat, burner is providing heat to the water, right? So here to rise the temperature of this water, okay, to rise the temperature of this water, okay, by 1 degree, okay, on 1 kg of liquid, the amount of heat required to rise the temperature of 1 kg of liquid by 1 degree, that you call as a specific heat. Okay, so assume this is a 2 kgs of water. Okay, let it be take 1 kg of water. Okay, to rise the temperature in this 1 kg of water, that means rise in temperature is 1 degree if you take. Okay, 1 degree centigrade. To rise the 1 kg of water heat by 1 degree centigrade, the amount of heat required you call as a specific heat. Okay, so the quantity of heat absorbed by or rejected. Okay, so this is a addition of heat condition. There is a other condition. If I have a hot water, okay, I keep it in a outside surrounding temperature. Okay, what I'm doing, I already have some hot water. I keep it in a surroundings. Assume surrounding temperature is 25 degrees centigrade. The water temperature is take a 80 degrees centigrade. Now what happened, because there is a temperature difference, definitely heat is flowing from higher temperature to lower temperature. This is a basic principle of heat, right? So here assume this is a 1 kg of water. Okay, is it 1 kg of water? Okay, to drop the temperature from 80 to 79 degrees centigrade. Okay, to drop the 80 to 79 degrees centigrade, how much amount of release of heat to the surroundings, that you call as specific heat. That meaning is that the quantity of heat absorbed or rejected by the system during a heating or cooling is measured, called specific heat. Okay, we have a formula to measure that one, that Q is equal to M into Cp into delta T. That means change in temperatures. That we represent short form is called MCP delta T. This Q is amount of heat, M is a mass of substance, Cp is a specific heat at constant pressure, delta T is change in temperature. That means you assume this is 80, this is 24. The difference of this one is called delta T. This is called a specific heat. Okay, so here Q is a heat gainer or loser, M is a mass of substance, C is a specific heat, and T2 minus T1 is difference in temperature, either in centigrade temperature or in kelvins. Right? In a specific heat, we have a two again classification. One is specific heat at constant pressure. Other one is specific heat at constant volume. Right? First one, specific heat at constant pressure. It is defined as the amount of heat required to rise the temperature of a unit mass or 1 kg or some unit mass of substance by 1 degree. That means 1 degree or unit degree in temperature variation in 1 degree change. At constant pressure conditions, you call as specific heat at constant pressure. Okay, we indicate this word Cp, that means C suffix P, and the units for this one is kilojoule per kg Kelvin. Kilojoule per kg Kelvin. Similarly, we have specific heat at constant volume. Okay, so what is this specific heat at constant volume means? It is defined as the amount of heat required to rise the temperature of unit mass of the substance by unit degree of change in temperature when it is in constant volume condition. That you call as a specific heat at constant volume. It is represented by C suffix V. The units for this one is same, kilojoule per kg Kelvin. The difference of these two is that just a very small difference, that is it happened at constant pressure condition, it happened at constant volume condition, that's it, nothing difference in it. Both are adding or removing of heat by for unit mass by unit degree of temperature. So formulas for Cp is Q is equal to mCp delta T. For this one, Q is equal to mCv delta T. That's it. The formula is same, but it happened when you are happened is in constant pressure condition, use this formula. When you do it is in a constant volume condition, you do this formula. Right. Next. So generally in most of the cases while we are doing discussing the thermodynamic systems, we have two things. One is specific heat of water and specific heat of air. These two generally we discussed. That is, if you take a specific heat of water is 4.186 kilojoule per kg Kelvin, okay, and specific heat at constant pressure of air is 1.005 kilojoule per kg Kelvin, and specific heat at constant volume for air you take as a 0.78 kilojoule per kg Kelvin. Right, this is the specific heat and the specific volume, and by this you can understand simple thing is we have only specific heat at constant pressure for liquids, but for gases we have both Cp, that means specific at constant pressure, and specific heat at constant volume, both we have. Okay, just so you please understand it, for solids and liquids we have only Cp values, but for the gaseous we have both Cp and Cv values. Okay, don't confuse for this. Okay, so this is you call as a specific heat conditions. Next, latent heat. So previously specific heat, this is a one form of heat. There is again one more condition is latent heat. What is a latent heat? So if you want to go for discussion of latent heat, it is defined as the amount of heat required to change the phase of system. Change the phase of system. So we discussed yesterday what is phase means. The physical presence of that system, which is in a, whether it is in a vapor state or a gaseous state or in a liquid state or in a solid state, to represent that one we call as a phase. So latent heat is discussed on the change of phases. Okay, it is defined as the amount of heat required to evaporate 1 kilogram of water at its saturation temperature or boiling point without change of temperature. Okay, we call as a latent heat. Okay, it is represented by the unit HFG. That means it is represented by enthalpy at Fg. That means a fluid and gas condition, and it is units for this one is kilojoule per kg. Right, the latent heat of vaporization of water, if we take as at a steam condition, is 2257 kilojoule per kg Kelvin. That means 2257 kilojoule per kg. Right, this is a latent heat condition. Right, now we'll discuss classification of latent heat again. So we have three classifications in a latent heat. Okay, in that one is latent heat of vaporization. Second one is latent heat of fusion. Third one is latent heat of sublimation. Okay, latent heat of vaporization, latent heat of fusion, latent heat of sublimation. What is these three? So first, example I am taking. Example, I have a water in a bowl. Okay, so initially water is in a liquid state. Okay, initially water is in a liquid state. Now I am adding a heat to this one. Nothing but by using some burner or anything, I am adding a water to heat to this one. Okay, by adding of heat, what happened? It rises the temperature to it is saturation point. It rises to the saturation point. Okay. So once it is reaches to saturation point, what happened? The water slowly get evaporated. So here the latent heat of fusion comes into picture is that at 100 degrees centigrade temperature, that means at a saturation temperature, the amount of heat added to the system to change the phase from liquid to gaseous, nothing but to steam, that you call as a latent heat of fusion. You understand, right? So at the same 100 degrees centigrade, without a change of temperature, I am adding a heat to the system. Okay, I am adding heat to the system. Okay, without changing a temperature, that you call as latent heat of fusion. Okay, so here I am not changing the temperature. At the same 100 degrees centigrade, I am changing the phase of system from liquid to gaseous. That you call as a latent heat of fusion. Next, sorry, this is you call as a latent heat of vaporization. I am extremely sorry for this. Right. So latent heat of vaporization. Okay, so we have a three classifications in a latent heat of vaporization. One is latent heat of vaporization. Next, latent heat of fusion and latent heat of sublimation. So what is these three? So I take the example of this one. I take some example. Okay, I have a water in a container. Okay, so I am adding a heat to this water. Okay, I am adding a heat to this water. Some amount of heat I am adding by using some burner or anything. Okay, so we know that water is get evaporated at 100 degrees centigrade. Okay, that is saturation point of water. Once it is reaches to the 100 degrees centigrade, it starts evaporating. That means it is convert the liquid form to the gaseous form. So once it is reaches to the 100 degrees centigrade, it starts evaporating. That state we call as a saturation point. So here a latent heat of vaporization is that the amount of heat required to change the phase of a system from liquid to gaseous, that you call as a latent heat of vaporization. Latent heat of vaporization. So I am not changing a temperature. Okay, at the same 100 degrees centigrade, the amount of heat required to change the water in a liquid form to steam. Okay, liquid to steam. That amount of heat you call as a latent heat of vaporization. Right? So this is the latent heat of vaporization. Next, we have latent heat of fusion. I am taking the same water. Okay, so now the water is at 25 degrees centigrade. Now I keep this water in a freezer. So due to that keeping in a freezer, the temperature drops and reaches to the 0 degrees centigrade. We know that when water reaches to the 0 degrees centigrade, what happens? It start solidifying. Okay, water get solidified, so that it is forms ice. Okay, so latent heat of fusion discuss that the amount of heat removed or addition from a system to change liquid to solid or solid to liquid. Okay, if it is changes from liquid to solid, that is that amount of heat removal, or if it is a changes from solid to liquid, the amount of heat addition. That's it. So that amount of heat either adding or removing to change the form to the solid to liquid or liquid to solid, that amount of heat you call as a latent heat of fusion. Okay, you take a water or any steel or anything, at a certain particular point it changes to one form to other form. but here the temperature you are taken at constant temperature. That means the that means change phase of temperature, either 0 or any temperature. That temperature condition only you are taking that as a input. That you call as a latent heat of fission. Next, one more thing, you have a latent heat of sublimation. So sublimation means there are a few components which directly convert from solid state to gaseous state. Example for this one is camphor. So here there is not much difference to the liquid state. It directly converts solid state to the gaseous state. So without a change in temperature, if any system changes its phase from solid to gaseous, gaseous to solid, that you call as a latent heat of sublimation. Okay, so all are latent heat of things, but in that again we have a classifications called latent heat of vaporization, latent heat of fusion, latent heat of sublimation. Right? Right. After this, we have to know some comparison of work and heat. So we have to compare the heat and work. Okay. So there are a few similarities in a work and heat. So here both work and heat are path functions. Also, it are inexact differentials. And we also say that all inexact differentials are path functions. Both heat and work are inexact differentials and both are path functions. So what is a path function? We know that it follows some path. If you draw some graph, it is follows some path. That we call as a path function. Next, both heat and work are boundary phenomena. Okay, so if you want to get a amount of heat, that means if you want to supply some heat or work, it is depends on boundary conditions, right? That's why we call it as a heat and work both are boundary phenomena. Okay, so and there is a one more common phenomenon is that heat and work both are associated with a process but not a state. It is associated with some process but not with a state. Okay, so it is unlike properties, work or heat has no meaning at a state. Okay, so there is a one more common comparison we can say how systems possess a energy but not work or heat. Any system possesses amount of energy but it not have some work or heat. So there are a few dissimilarities in that. In a heat transfer, temperature difference is required. Okay, definitely if it is a heat is need to transfer means definitely there is a temperature difference should be there. And in a stable system there cannot be work transfer. However, there is no restriction for the transfer of heat in a stable condition. That means if it is any thing is in a stable condition, you cannot expect any work from it. Right? See, simple example. So I keep the some rock on the ground. So if it is under rest, I cannot get any. I cannot expect any work from that rock. Or if I have something in a rest condition, we cannot expect any work from that. But even though I have work, that means even though heated system at a rest condition, you can expect some heat transfer. That means I have a example. I have some hot metal, okay, which is have a temperature of 200 degrees centigrade. Example you take. I have a hot metal at a 200 degrees centigrade. So I keep it at a atmosphere. So even though if it is in a rest condition, it releases the heat to the surroundings, right? It interacts the heat with the surroundings. So you can expect some heat transfer even though it is rest, but you cannot expect any work if it is a system at a rest condition. Okay. Next, the sole effect of external to the system could be reduced to rise of weight, but in the case of heat transfer, other effects are also observed. Okay, so this is a very common comparisons of both heat and work. Okay, and when you go for both heat and work, most rememberable points are that both heat and work are you can consider that. So I'm writing this one. Okay, so this is a work. Okay, examples for work. Okay, this is a example for the heat. Okay, assume this is system 1, which is for work. This is system 2. Okay, what I'm doing, so if this system is, from this system, if I get a some amount of work output, that you consider as a positive. But if you are supplying some work to the system, you consider it is a negative. Same in a heat. If you are supplying a heat to the system, it is a positive. If you are removing a heat from the system, you call as a negative. Okay, example for this system is, I taken as an example of IC engine. That means IC engine, it giving us amount of mechanical output. So nothing but it gives some mechanical work output. Okay, example for this one is refrigerator. Why it is consume the amount of mechanical work and give the refrigeration. Okay, so this is a IC engine, refrigerator are example for this condition. And the same heat also, heat applications also, it is, you can call it as a IC engine. So in a IC engine, what happened? It absorbs the amount of heat and give them mechanical output. That means you are supplying the heat to the system. To run it, we are supplying a amount of heat. And also, the example for this one also we can call as a refrigerator. That means it is, so refrigerator means it is cooling. That means to cool the substance, it is need to release the heat from that. That you call as a releasing of heat. That you call as a refrigerator as an example for this one. So you have to understand the sign conversion for the both. Okay. Next, these are a few important properties we'll discuss in the coming classes. And thank you, and have a nice day.
Like, share and subscribe. Hit the bell icon for more updates.